Hello, my name is Wong Yen Jun. This is the project title Detections of Surface Crack in Polylactic Acid Material using a Circular Split Ring Resonator. This is the table of content, which I will cover introduction, literature review, methodology, results and discussion, conclusion and recommendation, followed by reference and appendix. So I would like to highlight the background, problem statement, aims and objective of this project. Nowadays, non-destructive testing or NDT is a popular technique to detect the crack or detect in the defects in the materials. Microwave sensors is a popular technique of NDT. The size of crack can be characterized by measuring the variations of electromagnetic properties. In this project, different size of crack in sample models will be used to control the change in electromagnetic properties of the sample under test. Problem statement: inspection of surface crack in metallic and non-metallic materials is critical for quality assessment and maintenance. There are numerous NDT available to detect the crack in materials such as radiographic testing, visual testing, ultrasonic testing, and eddy current. Each technique possesses limitations and disadvantages. Only applicable for specific materials, expensive equipment, low sensitivity on small crack, high degree of skills experience. Objective 1. To design two simple, cost-effective, and high sensitivity of microwave sensor using a circular split ring resonators with coplanar waveguide. The second objective for this project is to measure the size of electric materials by analyzing the resonance frequency of S21 parameter and Q factor of split ring resonator. In the literature review, we will investigate what is the split ring resonator and how it works, what is a coplanar waveguide, what is a S parameter and how to calculate it, what are the existing non-destructive techniques, how do these planar microwave sensors work, and finally, what are the advantages of proposed planar microwave sensor. Split ring resonator is a common artificially fabricated structure in metamaterials. Normally, SRR consists of one or two concentric metallic rings with a gap in them etched on a dielectric substrate. The main purpose of SRR is to generate magnetic susceptibility in various types of metamaterials. The size of SRR is very small because small gap can exhibit greater capacitive values which can lower the resonance frequency and lead to the dimensions of the structure are smaller than resonant wavelength. A coplanar waveguide (CPW) is a planar electrical transmission line that can be manufactured using printed circuit board technology. It consists of a center strip of thin metallic film deposited on the surface of a dielectric slab separated from a pair of ground planes. This feature simplifies manufacturing and allows quick and low-cost characterization using on-wafer technique. CPW can be used as different type of component in the circuit. S parameter, also known as the scattering parameter, it is used to describe how linear electrical networks, such as parts, circuits, and systems in high-frequency or microwave engineering behave. It is a very useful parameter in a variety of electrical engineering fields like electronics, communication system design, and in particular microwave engineering. The S parameter matrix for the two-port network is undoubtedly the most often employed. There are two main types of S parameter, which are S11 and S21. S11 is referred to reflection coefficient, S21 is referred to transmission coefficient. For NDT, it is defined as the determinations of the physical conditions of an object without affecting that object's ability to fulfill its intention function. This NDT technique is popular and widely used in testing composite materials. Applications for composite NDT may be found in a variety of fields, such as manufacturing, aerospace and defense industries, nuclear sector, characterizations of composite faults. How do these planar microwave sensors work? Microwave near-field sensors have been considered as the main choice of sensors due to their cheapness, miniaturization, selectivity, and sensitivity. The mechanism of microwave near-field sensor is measuring the change in the resonance frequency due to the field interactions with sample under test. They can make sufficient penetration inside most dielectric materials and enable high-resolution sensing. They have been utilized to design near-field sensors for many applications due to strong near field of this electrically small resonator. The size or width of the crack increases significantly, the resonance frequency will shift to the right. What are the advantages of proposed planar microwave sensors? These are the literature reviews for the past study. For the methodology of this project, we have several stages. First stage, we design and simulate the planar microwave sensor in HFSS. The second stage, fabrications of design planar microwave sensor. Stage 3, with design and model making. Stage 4, measure the width of crack using the design planar microwave sensors. For stage 1, we design and simulate planar microwave sensor in HFSS. The design is as shown in figure 3.1. This is the design of planar microwave sensor for the top view. Figure 3.2 shows the design of planar microwave sensor at the bottom view, and figure 3.3 shows the design of planar microwave sensor from the bottom view as well. Figure 3.4 shows the design of a planar microwave sensor top view with a solution type layout as driven model. Step 3 involve the parametric model geometry materials, which include boundaries and excitation. Step number 4 for stage 1, it includes the setup of analysis solutions and frequency sweep. Step 5 shows the results of 2D report field. Results after simulations can be obtained from this stage. For stage 2 fabrications of design planar microwave sensor, we have two figures to show it, the top view and the bottom view respectively. For stage 3 design and model making, figure 3.515 shows the design polylactic exit PLA materials model without crack. For figure 3.16, the design polylactic acid materials model without crack from the top view. From figure 3.17 to figure 3.20, we are showing the design PLA materials with different dimensions of crack. Figure 3.22 is the 3D printer. Figure 3.23 shows the design polylactic acid materials model. For stage 4, we measure the width of crack using the design planar microwave sensors. For the result part, I would like to highlight the characteristic impedance of the CPW. From figure 4.1, it shows the simulations of characteristic impedance for the FR4 substrate using HFSS. For figure 4.2, simulations of characteristic impedance for the RO3210 substrate using HFSS. This is the resonance frequency of design planar microwave sensor. Figure 4.3 shows the simulations of resonance frequency for the FR4 substrate using HFSS, and figure 4.4 shows the simulation result of resonance frequency S21 for the RO3210 substrate using HFSS. Figure 4.5 shows the measurements of resonance frequency S21 for the FR4 substrate using VNA, and figure 4.6 shows the measures of resonance frequency for the RO3210 substrate using VNA. The resonance frequency of design sensor loaded with the SUT are shown in graph 4.1 and 4.2. For graph 4.3, the graph of transmission coefficients for numerous width of crack in the models they are shown here, And for graph 4.4, the graph of S11 quality factor for numerous width of track in the models are shown. Graph 4.5 shows the frequency response of the design sensor, the version RO3210 for different width of track in the models. Sensitivity of design sensors are shown in this table. For comparison, for the substrate of FR4 and RO3210, we obtain a change in resonance frequency 16 for FR4, 2.5 for RO3210. The change in width of track is the same, 5 mm, and the sensitivity for FR4 is 3.2 as compared to 0.5 for RO3210. Figure 4.7 shows another sample grain which has the same width of crack is tested. For figure 4.8, the sample is put on SRR and measured by using VNA. Figure 4.9 shows the sensor sensitivity test. The S21 report for the design sensor used an FR4 substrate with 4 mm crack model. And this is for the versions of RO3210. So by comparisons, the width of crack measured shows a very less difference. It's only by 0.5 mm. So from the equations, it is calculated as x equals to 4.76 mm. For RO3210, we obtain x equals to 5 mm. So this is the comparisons of the design sensor FR4 and RO3210. Conclusion and recommendation. The objective of the project have been achieved. The relationship between width of crack and resonance frequency of planar microwave sensor have been discovered. The sensitivity of sensors are 2.9 for FR4 and 0.5 MHz per millimeter. The unknown width of crack can be identified by observing the shift of resonance frequency. Recommendation. It is recommended that crack measurements be performed in the same locations with similar environmental conditions. The same density and shell of sample is highly recommended. The design model should be placed on SRR and fully cover the SRR. The current design can be further enhanced by utilize higher grade coaxial cable with a shorter length to avoid impedance mismatch. Thank you.